Hey! Welcome to Pixel Perception. I am Aria, your system design guide for this series, and I promise you, by the end of today, you are going to think about software in a completely different way.
And I am Leo. I am the guy who asks all the embarrassing questions that everyone secretly wants to ask but is too afraid to. We make a pretty good team. Honestly.
Today we are starting a deep dive into one of the most famous technical books ever written, Designing Data-Intensive Applications by Martin Kleppmann. It is the one book that every senior engineer swears by. And we are going to explain it so clearly that even a complete beginner, someone who has never thought about system design before, can understand and love it.
No boring lectures. No confusing jargon dropped without explanation. We use real diagrams, real-world analogies, interactive quizzes, and sound effects. This is not a course you passively watch. You actually participate in it. And you just might have fun. Let's go.
Let's start with the most fundamental question. Why do modern applications need all this complex engineering in the first place?
Aria. Before we dive into chapters, I want to understand something really basic. Why do we even need this big complicated book? Is not building software just writing code?
Back in the 1980s, that was actually mostly true. Software was compute intensive. The hard problem was raw mathematical computation. Weather simulations, physics engines, cracking encryption codes. The CPU was always running at 100%. You just needed faster processors and you were done.
And today, apps like Instagram or Uber do not seem mathematically heavy at all. But they still need hundreds of servers and an enormous amount of engineering. So what is the actual challenge now?
Because today the hard problem is data, not computing power. The sheer volume of it, the speed at which it flows, and how structurally complex it has become. A modern social media app stores billions of posts, serves hundreds of millions of users simultaneously, and needs to retrieve the exact right content in under 100 milliseconds. We call these data-intensive applications. And Kleppmann's book is entirely dedicated to teaching you how to build them properly. Here is something fascinating. Every application, no matter how complex, is built from the same handful of building blocks. Here is the first big insight of the entire book. No matter how fancy the application, whether it is a tiny startup or Google itself, every software system is secretly assembled from the same standard building blocks.
Like Lego pieces. So what are these building blocks actually?
Exactly like Lego. The first block is a database, something that stores your data permanently so you do not lose it when you restart. The second is a cache, which remembers the results of expensive operations so you do not repeat them unnecessarily. Third is a search index for doing fast keyword lookups across billions of records. And finally, stream and batch processors for handling large amounts of data asynchronously in the background without slowing down the main application.
So our entire course is really about understanding how each of these blocks works internally. and then how to combine them effectively without the whole architecture collapsing under real-world load.
Let us look at the complete roadmap for our entire series. The book divides into 3 epic parts. Exactly right. The book is split into 3 major parts. Let me walk you through our complete series roadmap so you always know where you are in the journey. Part 1 is called Foundations of Data Systems. This is where we understand what happens inside a single machine, before we even think about distributing anything across multiple servers.
And that is what we are covering today, Chapter 1. After today, what else is in Part 1?
After today's Chapter 1 on the 3 holy pillars of system design, we tackle Chapter 2 on data models, the legendary battle between relational SQL, document NoSQL databases like MongoDB, and graph databases like Neo4j. Chapter 3 Tiers open the hood of storage engines to understand B trees versus LSM trees and why the choice matters enormously. And Chapter 4 covers data encoding, how systems can evolve their data schemas over time without breaking backwards compatibility, using formats like protocol buffers and Apache Avro. Part 2 is where things get genuinely mind-bending. Distributed systems.
Part 1 already sounds incredibly rich. What happens in Part 2? I have heard terms like sharding and replication thrown around in senior engineering interviews, and I honestly just nod and pretend to understand.
We are going to fix that completely. Part 2 is called Distributed Data. This is where a single server is no longer enough and you have to spread your data and your workload across multiple machines around the globe. Chapter 5 covers replication, making safe copies of your data on multiple servers so nothing is permanently lost when one machine goes down. Chapter 6 is partitioning, also called sharding, splitting a giant dataset into smaller manageable chunks so no single server gets overwhelmed.
And the infamous cap theorem and consensus stuff. Is that in Part 2 as well?
Chapter 7 covers transactions and the famous ACID guarantees. Chapter 8 is called The Trouble with Distributed Systems, which is honestly one of the most fascinating chapters in all of computing. It covers clocks that drift and lie, networks that silently drop packets, and machines that cannot agree on anything. And Chapter 9 shows how distributed systems can eventually reach consensus using algorithms like Paxos and Raft. These are the algorithms powering Google Spanner and ECT. And Part 3 ties it all together into the largest, most powerful data pipelines in existence. And then finally Part 3. Derived data. This is where we zoom all the way out and look at massive enterprise data pipelines that tie all the distributed databases we learned about into coherent, powerful systems. This is honestly the chapter range that separates mid-level engineers from staff and principal engineers.
Like the big data stuff. MapReduce, Kafka, Spark.
Chapter 10 is batch processing, MapReduce and Apache Spark that crunch through terabytes of historical data overnight and produce analytical reports. Chapter 11 is stream processing, systems like Apache Kafka and Apache Flink that react to real-time events in milliseconds as they happen. And Chapter 12 ties everything together with a vision of the future, how we unbundle the traditional monolithic database into specialized components and build for an ethical, transparent, data-driven world.
Okay. That entire roadmap already sounds like the most exciting engineering education I have ever heard. But you said today is chapter 1, the 3 holy pillars. I am ready. Let us start.
Before chapter 1 begins, let's do a quick check. This first quiz is based purely on the intro we just covered. Before we officially open chapter 1, let us see if you were paying attention during the introduction. One quick question. No pressure at all, this is for fun and for keeping those neurons active.
Yes. That is the exact insight the whole book is built on. The amount of data, the speed it moves, and its complexity are what bring modern systems to their knees, not CPU cycles.
Excellent. Chapter 1 officially open. This is where Klepman asks the most important question in software engineering. How do you build software that is genuinely good? Not just software that works when everything goes right, but software that is trustworthy, capable, and livable for the engineers who need to maintain it day after day for years.
And his answer is 3 non-negotiable properties that every serious software system must have. What are they?
Property 1. Reliability. The system must continue working correctly even when things go wrong. Hardware breaks. Code has bugs. And humans make mistakes, but the user should never notice any of it. Property 2. Scalability. As usage grows from 100 users to 100 million users, the system must have well understood strategies for handling that growth. And property 3. Maintainability. Over time, many different engineers will work on this system, and they should all be able to do so productively and without misery.
These 3 properties sound almost common sense when you say them out loud. But I have a feeling they are hiding enormous depth and subtlety. Let's go through each one seriously. Starting with reliability.
Pillar 1. Reliability. But first, 2 words that everyone confuses. Fault versus failure. To understand reliability properly, we need to nail down 2 words that sound almost the same but mean completely different things. Fault and failure. This distinction comes up constantly in senior engineering conversations and interviews. And mixing them up is a quick way to lose credibility.
What is the difference? They seem basically synonymous. Something breaks.
Not at all. A fault is when one individual component of your system deviates from its expected behavior. A single hard drive starts throwing checksum errors. One CPU core overheats and gets throttled. One network switch drops some packets. A fault is local, isolated, and at cloud scale. Completely normal. Hardware faults happen every single day at Google and Amazon.
And a failure is different.
A failure is when the entire system stops providing its required service to the end user. The website goes completely offline. Customers cannot make purchases. Messages fail to deliver. A failure is something the user experiences and complains about. Our entire engineering mission with reliability is to build systems where faults can and do happen all day long, yet the user never feels any impact whatsoever. So where do faults actually come from? Category 1. Hardware.
So where do these faults actually come from? What breaks in the real world?
Category 1 is hardware faults. Hard drives fail. RAM modules develop random bit errors where a single bit silently flips from 0 to 1 for no reason, causing subtle data corruption that only manifests weeks later. Power supplies blow. Networking cables get accidentally severed. And at the scale of a cloud platform running 10,000 or 100,000 servers. These events happen literally every single day. This is not hypothetical, it is mathematically inevitable.
So how do we defend against hardware just randomly dying on us at any moment?
The classic answer is hardware redundancy. RAID disk arrays that mirror data across multiple drives so one dying disk is completely invisible. Dual power supplies so one power unit failure does not kill the server. Hot swappable components. And in modern cloud architecture, we go even further, we replicate data across multiple independent availability zones, which are physically separate data centers in different buildings or even different parts of the city. If one entire building loses power or catches fire, traffic silently redirects to another zone in milliseconds. Users see nothing. Category 2 of faults. Software errors. And these are far scarier than hardware faults. The second and more dangerous category is software errors. And here is the crucial thing that makes them truly scary compared to hardware faults. Hardware failures are usually random and completely independent of each other. One server's disk fails and it has absolutely nothing to do with another server's disk. But software bugs are systematic and correlated, they live in code that runs on every single server in your fleet.
Correlated how? You mean one bug can take down thousands of servers all at the same time?
That is exactly what happens. Leap year bugs, where a programmer makes a date calculation mistake and the moment February 29th arrives, thousands of servers running the identical faulty code all crash simultaneously. Memory leaks that silently consume a tiny bit of extra RAM on every server over days and weeks, until they all hit their memory limit simultaneously and crash together. Runaway retry loops, where one service starts failing, causing another service to retry thousands of times per second, which overloads the first service even further, a cascade that can bring down an entire data center.
That sounds genuinely terrifying. How do you even begin to defend against bugs that can take down the whole system at once?
Honestly, there is no single silver bullet. You use process sandboxing so one buggy service cannot crash everything else around it. You invest heavily in automated test suites that catch regressions before they reach production. You implement circuit breakers that automatically cut off communication to overloaded services before they cascade into total failure. And most powerfully, you build rich real-time telemetry, detailed metrics, structured logs, and distributed traces so you know the instant something starts behaving differently from normal, long before users are impacted. Category 3. Human errors. And this is the big one responsible for most real outages.
You mentioned 3 categories of faults. What is the third?
The third, and by a wide margin the most common cause of major outages in real-world production systems, is human error. Studies and post-mortem analyses consistently show that mistakes made by human operators are responsible for over 70% of major cloud outages. Not hardware. Not software bugs. Humans. Engineers type the wrong configuration command and accidentally take down a production service. Someone runs a database migration script that deletes the wrong table. A developer pushes code that was never tested under production conditions.
We obviously cannot fire all the humans. So how do you design a system that is robust against its own operators making mistakes?
You design with the absolute certainty that humans will make mistakes, and you build guardrails everywhere. You provide sandbox staging environments that are visually and functionally identical to production but completely isolated, so engineers can practice dangerous operations without any risk. You enforce granular IAM permissions so no single engineer can accidentally wipe an entire production database with one command. You mandate that destructive operations require 2-person approval. And most powerfully, you build fast automated rollback tools if a bad deployment goes out at 2 in the afternoon. You can completely reverse it in 10 seconds without waking up the whole company at 3 in the morning. Quiz time. Let us test the fault versus failure distinction.
Let us make absolutely sure you understood the fault versus failure distinction, because this is one of those concepts that comes up in system design interviews all the time. Think carefully before clicking. There is one clearly correct answer. Perfect. One server died, that is the fault. But the load balancer instantly rerouted traffic to healthy servers and users never noticed a thing. That is fault tolerance in action. Beautifully done.
Before we move to Pillar 2, let me give you the complete reliability picture in one clean table. Study this carefully. The 3 fault categories and their corresponding defense strategies are something every system designer needs burned into memory. Hardware faults need hardware redundancy. Software errors need telemetry, sandboxing, and circuit breakers. Human errors need process guardrails, permission controls, and fast rollback.
The core takeaway from all of this: a reliable system is not a system where nothing ever breaks. Hardware will break. Bugs will slip through. Operators will make mistakes. A reliable system is one that has been designed from the ground up to gracefully absorb all of these faults so that end users never feel the impact. That distinction is the entire philosophy of reliability. Are you ready for Pillar 2?
Pillar 2. Scalability. And the first thing we need to do is throw away your current definition of the word. Pillar 2. Scalability. Leo. I want to try something. If someone says to you in an interview confidently that their system is totally scalable, what does that mean to you?
I would assume it handles lots of traffic. It does not crash under load. It is fast. Something like that.
And here is what Kleppmann says. The statement "our system is scalable" is completely and utterly meaningless without much more context. Scalability is not a one-dimensional binary property that you either have or do not have. It is the system's ability to cope with increased load and to answer whether it is scalable. You first must specify what kind of load, how much is it growing, and what performance trade-offs are you accepting in order to handle more of it.
So we need to be very specific. And to be specific, we first need to quantify our load in concrete numbers.
Exactly. These numbers are called load parameters. The right load parameter depends entirely on what kind of system you are building. For a web server, requests per second. For a relational database, the ratio of read operations to write operations. For a chat platform like WhatsApp or Discord, the number of simultaneously active users in a channel. For an in-memory cache like Redis, the cache hit rate. Identifying and tracking your specific load parameter is the very first step to designing for scalability. To see load parameters in action, let's look at one of the most famous architecture stories in tech history: Twitter. The book uses Twitter as one of its most brilliant and instructive case studies for understanding load parameters and scalability trade-offs. Let me set up the scenario. Twitter had two core operations that had wildly different load characteristics.
What were the two operations?
Operation 1. Post a tweet. A user publishes a message and it should appear on the home timeline of every single person who follows them. Twitter was handling about 4,600 of these writes per second on average, peaking at 12,000 during major events like the World Cup. Operation 2. Read the home timeline. A user opens the app and needs to instantly see the most recent tweets from all the accounts they follow. Twitter was handling about 300,000 of these reads per second. Notice the enormous imbalance: 65 reads for every single write.
So reads massively outnumber writes. The raw volume of both seems manageable for a modern database. Where is the actual hard engineering problem hiding in this picture?
The hard problem is something called fan-out. Let me show you why Twitter's first obvious approach completely fell apart. The challenge hidden in these numbers is called fan-out. When you post one tweet, it needs to be visible to potentially hundreds or millions of followers. This fan-out effect is what made Twitter's engineering genuinely difficult. Their original approach was the obvious one: a traditional relational SQL database. When you post a tweet, the system inserts a single row into a tweets table. Dead simple. Very fast, right?
That sounds perfectly reasonable. A simple insert. What went wrong?
Reading the home timeline was the catastrophic problem. When you opened your Twitter app, the server had to execute an enormous SQL query. Find all the user accounts you follow. Fetch their most recent tweets. Sort everything by timestamp. And return the final merged list. Doing this SQL join computation 300,000 times per second, each one requiring expensive traversals across billions of rows across multiple tables, was absolutely melting their database servers. This is what caused the famous Twitter fail whale error page.
So the problem was that all the work was happening at read time. And with 300,000 reads per second, computing everything on demand was completely unsustainable. They needed to shift the work somewhere less painful. What was their next attempt?
Their second approach was brilliantly clever but came with a dark, unexpected catch. Twitter's second approach flipped the entire problem on its head. Instead of computing the timeline at read time, they moved all the work to write time. They gave every single user an in-memory mailbox, a pre-computed, pre-sorted timeline cache stored directly in Redis. When you post a tweet, the system immediately looks up all of your followers and pushes your new tweet ID into each of their personal mailbox caches right then and there.
Oh, that is genuinely clever. So when someone opens their app, they just grab their pre-made mailbox, no expensive join needed. Just a simple read from a cache.
Exactly. Reading the timeline became almost instantaneous, just a simple cache lookup. But there was a dark catch lurking in this design. Think carefully about this question. What happens when someone with 30 million followers posts a single tweet?
Oh no. You would have to write that one tweet into 30 million different mailbox caches. All at once.
In a matter of seconds. Yes. A single celebrity posting one short tweet would instantly trigger 30 million simultaneous write operations flooding the system. It caused massive latency spikes, cascading queue backlogs, and data center chaos. This became known as the celebrity problem. The push model worked perfectly for ordinary users with a few hundred or a few thousand followers, but it completely shattered under the weight of accounts with millions of followers. And this is where Twitter did something genuinely brilliant. They stopped asking either or and started asking both and. This is where Twitter did something architecturally beautiful. They stopped asking the binary question push or pull and asked instead, can we use both? Selectively. For different types of users.
So they split their users into two categories.
Exactly. For the vast overwhelming majority of users with normal follower counts a few hundred, a few thousand, they continued using the push model. Your tweet gets fanned out into your followers' pre-computed cache mailboxes immediately. Fast. Clean. Simple. But for users flagged internally as celebrities, accounts that have millions of followers, their tweets are not pushed anywhere at right time. Instead, they are stored in a completely separate celebrity tweet table.
And then when someone opens their timeline,
their pre-computed cache gets instantly loaded for all the regular accounts they follow. That is the fast push portion. And then simultaneously, the system runs a small targeted pull query specifically for any celebrity accounts they follow, and merges those results in sub-millisecond reads for everyone. No celebrity write storm. This is what engineers call a hybrid architecture, and it is exactly the kind of intelligent trade-off analysis that gets you hired as a senior engineer at top technology companies. It shows you can reason about real-world constraints rather than just applying textbook solutions. Quiz time. The Twitter fan-out problem is one of the most discussed case studies in all of system design.
The Twitter architecture story is one of the most famous system design case studies that comes up in senior engineering interviews at every major tech company. Let's see if you absorbed the core insight. Take your time, the answer requires careful thinking. Nailed it? One celebrity tweet triggered millions of simultaneous cache write operations, a write storm that overwhelmed the data center. The hybrid solution separates celebrities from normal users to prevent exactly this. Brilliant.
Now let's talk about measuring performance. And first, let's clear up two words that almost everyone uses incorrectly. Now let's talk about measuring system performance. Leo. Quick question. If I send a request to a server and measure how long it takes, am I measuring latency or response time?
Honestly, I have always used those two words completely interchangeably. Is there a difference?
Most people do use them interchangeably, but they are technically distinct. Response time is what the client actually measures. The total duration from the moment a request is sent to the moment the final response is received. It includes everything. The time sitting in a queue. The actual server processing time. Any garbage collection pauses. The network round trip time. And any serialization overhead.
And latency is something different.
Latency is technically just the queuing delay, specifically how long the request sat waiting before any processing even started. Think of it exactly like a doctor's office. Latency is the time you spend sitting in the waiting room before the doctor even calls your name. Response time is the entire visit from walking through the front door to walking back out. The distinction matters because they have very different causes and very different solutions. And now for one of the most important lessons in performance engineering. Why you should never trust the average. Here is a trap that catches almost every junior engineer. If your manager walks over and asks how fast is our website today, the wrong answer and the answer that will make experienced engineers wince is to report the average response time. The average is a deeply misleading number. Here is a concrete example. Imagine 99 requests complete in 10 milliseconds each. But one single request takes 10 full seconds. The average looks totally acceptable at around 100 milliseconds. But one real user just had a catastrophically terrible experience.
So what do experienced engineers use instead of averages?
Percentiles. You take all your response time measurements, sort them from fastest to slowest, and look at specific points in that distribution. The P50 is the median. 50% of requests are faster than this value. But for understanding how bad things can get for real users, you look at P95, P99, and P999, the 95th, 99th, and 99th percentile. If your P99 is 1.5 seconds, that means 1 out of every 100 requests is making someone wait more than 1.5 seconds. That is your most frustrated user.
Why do companies care so deeply about those P99 slowest users? Is 1% really worth all the engineering effort?
Amazon famously discovered through rigorous experimentation that a mere 100 millisecond increase in response time directly reduced their total revenue by 1%. 100 milliseconds barely noticeable to a human cost them hundreds of millions of dollars per year. And here is the cruel irony. The customers hitting those P99 slow responses are very often your most valuable users. They have enormous shopping carts, years of purchase history requiring complex personalization, and thousands of product recommendations to compute. The slowest requests happen to the highest value customers. So what actually causes those P99 tail latencies? The answer is something called head-of-line blocking.
What actually causes that 1 in 100 request to be so much slower than all the others? Where does the extra time come from?
One of the most significant culprits is head-of-line blocking. Let me give you an analogy that will make this permanently clear. Imagine you are at a grocery store checkout. You have a single item, one chocolate bar. The checkout should take you 15 seconds maximum. But the person directly in front of you has an overloaded cart and is disputing the price of every single item with the cashier. You are completely stuck.
And the same thing happens with server requests.
Every single day at scale. A slow database query. A sudden garbage collection pause. A network retransmission timeout, and every single request that arrives at the server during that period gets queued behind it. Those subsequent requests are not inherently slow. They are simply stuck behind the slow one. And in distributed microservice architectures where loading one web page might require calling 30 or 40 different backend services if just a single one of those services hits its P99 tail latency, the entire end-user page load becomes slow. A tiny problem in one service cascades into a terrible experience for the user. Okay, so load is growing and performance is degrading. What are our options for fixing it? When our load parameters are growing and our performance metrics are degrading, we have two fundamental philosophical approaches for coping. The first is scaling up, also called vertical scaling. You replace your server with a more powerful one. More CPU cores. More RAM. Faster NVMe storage. The incredible advantage is simplicity. No distributed system complexity. No coordination problems. No network partitions. Just faster hardware.
So vertical scaling sounds great. What is the problem with it?
Two major problems. First, it is exponentially expensive. Doubling the performance of a server often costs 4 or 8 times as much money. Second, there is a hard physical ceiling. At some point, you simply cannot buy a bigger machine. The most powerful server money can buy will still not handle the traffic of a Google or a Facebook. That is where horizontal scaling out comes in. You distribute your load across many smaller, cheaper commodity servers. Each machine handles a fraction of the total work. When traffic doubles, you add more machines. This scales to virtually any size.
And modern cloud platforms like AWS and Google Cloud combine both approaches with elastic auto-scaling, automatically adding machines when traffic spikes during the day and removing them at night when traffic drops. Pay only for what you actually use. That is genuinely elegant engineering.
Another quiz. This one tests whether you truly understand why percentiles matter more than averages. This is a classic question that separates engineers who understand performance from those who just use monitoring dashboards without thinking. Take a careful look at the numbers before clicking. The math is simple, but the insight is profound.
Yes. The P99 is 10,000 ms 10 full seconds. 1 in 100 users is waiting 10 seconds. The average hid this completely. This is exactly why percentiles matter so much for SLAs at companies like Amazon and Google. You nailed it.
Let me lock in the complete scalability mental model before we move to our third and final pillar. 4 core concepts. You now understand that most people who call themselves engineers do not think about precisely. Load parameters. You cannot design for scale without first quantifying exactly what is growing. Percentiles, not averages. Averages lie and hide your worst user experiences. The fan-out problem. A single write propagating to millions of places requires creative hybrid architectures like Twitter's solution. And the scale-up versus scale-out trade-off. Vertical scaling is simple but limited. Horizontal scaling is unlimited but complex.
That is a genuinely solid foundation for reasoning about scalability in any architecture conversation. And now for the third pillar, the one that most engineering books ignore completely. But that Kleppmann rightly argues is equally important as the other two. Maintainability. Let's go.
Pillar 3. Maintainability. And the first thing we need to do is confront a truth that most engineers find uncomfortable. Here is something that computer science universities almost never teach, and it fundamentally changes how you should think about software design. The initial development of a software system, all the exciting decisions. Building from scratch. The greenfield work typically represents only about 10 to 20% of its total cost over its entire lifetime.
Wait, only 10 to 20%. Where does the other 80% of the cost actually go?
Into ongoing maintenance. Fixing bugs that only appear under very specific rare combinations of conditions. Investigating mysterious failures that happen once a month at 3 in the morning. Adapting the system when it needs to integrate with new platforms or new regulatory requirements. Adding features that the original architects never anticipated when they designed the data model. Keeping up with critical security patches. And onboarding new engineers who have never seen the code base before and need to be productive within weeks.
I have definitely worked on code bases that felt like wading through chest-deep concrete. Everything takes 3 times longer than it should. You are afraid to change anything because you do not know what else might break. Is there a principled way to design systems so that maintenance does not become an engineering nightmare?
That is precisely what Kleppmann addresses with 3 design principles that directly and deliberately fight the maintainability battle. Operability, simplicity, and evolvability. Maintainability Principle 1. Operability. Making life genuinely easy for the people who run your system. The first principle is operability. Make life truly easy for the operations and site reliability engineering team. The old engineering wisdom says good operations can often work around limitations in bad software. But bad operations will destroy even the best designed software in the world. The people responsible for running your system need to be able to understand it, monitor it in real time, and fix it effectively when it breaks at 3 in the morning.
What does that look like in practice? What makes a system operationally friendly as opposed to operationally hostile?
Rich telemetry, structured logs that are queryable, metrics dashboards that show trends, and distributed tracing that lets you follow a single user request as it flows through 20 different microservices. Clear self-documenting interfaces so engineers do not need to read internal source code to understand what a service does. Avoiding hidden side effects, dangerous global state, and action at a distance behavior that makes systems unpredictable. And most importantly, automation for all routine tasks. Deployments, database backups, certificate renewals, and failovers should all happen automatically. Human judgment should be reserved exclusively for genuinely novel situations that automation cannot handle. Maintainability Principle 2. Simplicity. The active, deliberate fight against accidental complexity. Principle 2 is simplicity specifically. Actively fighting accidental complexity. As software projects grow and age, they naturally accumulate complexity that was never inherent to the problem they were solving. This is called accidental complexity. Workarounds for old bugs that nobody cleaned up. Special cases for edge conditions that no longer exist. Quick fixes from a 5-year-old deadline that became permanent. Global state that no one remembers the purpose of.
Every large code base I have ever touched has exactly that feeling. 1,000 special cases. Nobody knows what half the configuration flags actually do. You are terrified to change anything because something completely unrelated might randomly break.
Kleppmann calls that state a big ball of mud. And the most powerful solution is abstractions. A well-designed abstraction hides a massively complicated internal implementation behind a clean, simple, easy to understand interface. The greatest and most impactful abstraction in the entire history of computing is SQL itself.
SQL is an abstraction.
A perfect one. When you write select users where age is greater than 21, you have absolutely no idea whether the database is navigating a B-tree index, or reading a sorted LSM tree, or using a hash index, or doing a full table scan. You do not need to know. The SQL abstraction completely hides all of that internal complexity. And finding excellent abstractions, the kind that truly capture the essential nature of a problem and remain useful as requirements evolve, is the rarest and most valuable skill in software engineering. Maintainability Principle 3. Evolvability. Building for a future you cannot predict. Principle 3 is evolvability. Make change easy. This is perhaps the deepest and most underappreciated principle of the three. In real-world software development, requirements never ever stay static. Your company pivots its entire business model. New data privacy regulations arrive that require you to completely rethink how you store user information. User behavior shifts in ways nobody predicted. a new technology emerges that makes your current approach obsolete.
In regular application code, we handle this with refactoring and agile development. But in data systems, I imagine change is much more difficult because of all the historical data already sitting in production databases.
You are exactly right. And this is the insight that takes years to truly internalize. You can refactor application code in an afternoon. But if you have 10 terabytes of data in a specific schema and business requirements change such that you need to restructure that schema, that is potentially a multi-month engineering project requiring careful coordination, staged migrations, and backward compatibility windows. Evolvability means designing your data systems from day one to support schema migrations without downtime. Backward compatible data formats so old code can still read new data. And the architectural flexibility to swap out one storage engine for a better one without rewriting every downstream application.
So it is about designing today with a clear-eyed assumption that tomorrow's requirements will be completely different from what we expect.
Not just an assumption, an absolute certainty. Requirements will change. The question is only when and how dramatically. Chapter 4 of this book is dedicated entirely to the technical machinery of data encoding and schema evolution, the concrete tools that make evolvability achievable in practice. But first, one more quiz. Final quiz on maintainability. 3 principles. 1 question. Think carefully about which one applies. 3 principles. Operability, simplicity, and evolvability. They are all part of maintainability, but each has a distinct focus. Read this question carefully before clicking. The wording matters. Yes. Simplicity through abstraction. SQL hides massively complex storage internals behind one clean interface. Users don't need to know B trees exist to query a database. That is a perfect abstraction fighting accidental complexity. Well done. We just completed Chapter 1 of Designing Data-Intensive Applications. That was a genuinely dense and important chapter, and you made it all the way through. Let me give you the complete mental model that you now carry as a system designer.
Every serious software system must answer 3 questions honestly. First, is it reliable? Does it absorb hardware failures, software bugs, and human mistakes without any of that pain reaching the end user? We learned about the 3 fault categories and how to defend against each. Second, is it scalable? Do we have quantified load parameters? Do we track percentiles rather than averages? And do we have deliberate strategies for handling growth like Twitter's hybrid push-pull architecture?
And third, is it maintainable? Can the operations team monitor and manage it without suffering? Is it simple enough through good abstractions that a new engineer can become productive in it within weeks? And can it evolve gracefully over the next 5 or 10 years as requirements inevitably change? When a system has all 3 of these properties, it is what we call a well-designed data-intensive application. That is the entire thesis of the book.
And I want to say, if you absorbed and understood everything we covered today, you are genuinely ahead of a large majority of people who call themselves system designers in the industry. This vocabulary and this framework are the foundation that everything else in this course builds upon.
Before we wrap up, let me give you a taste of what is coming in our next episode. In our next episode, we go deep on Chapter 2, Data Models and Query Languages. And I have to be honest with you, this one gets a little heated, because it is one of the oldest and most passionately argued debates in all of software engineering.
The SQL versus NoSQL debate.
Yes. We will go deep on relational databases, why SQL has completely dominated the industry for over 50 years and what makes it so enduringly powerful. Then we will look at document databases like MongoDB, when they genuinely and specifically beat SQL, and when the NoSQL hype is leading engineers astray. And we will explore graph databases like Neo4j, which can express certain types of connected data relationships in ways that would require nightmarish chains of SQL joins to replicate. You will finally have a real, principled answer to the question of when to use each type.
I am very much looking forward to finally having a real informed answer to the SQL versus NoSQL question, one that goes far beyond the unhelpful answer of "it depends." Make sure you subscribe so you do not miss it. Episode 2 is going to be genuinely great.
We put a huge amount of love and genuine effort into designing these interactive, visual, addictive lessons so you can learn the most important engineering concepts in a way that actually sticks and actually makes sense. If this style of learning resonates with you, please hit like on this video. It costs you literally nothing and it helps the YouTube algorithm share this content with other engineers and students who need it.
And hit subscribe. We have episodes on data models, storage engines, distributed replication and consensus, batch and stream processing, all coming in this series. Every single episode is built the same way: visual, interactive, designed to make you think. You genuinely do not want to miss any of them.
And if you know one person, one friend, one colleague, one study partner who is preparing for system design interviews or just wants to level up as an engineer, please share this video with them. A single share might be the most meaningful thing you do for someone today. This is exactly the kind of content we all wished existed when we were learning this material.
And drop a comment below. Tell us which concept from today surprised you the most. The Twitter fan-out story? The fact that averages lie and you should use percentiles? The revelation that human errors cause over 70% of major outages? We genuinely read every comment. This is Pixel Perception, and we will absolutely see you in the next one.
Congratulations! You have completed episode 1 of the Pixel Perception System Design series. See you in Chapter 2.